All right, so we have been discussing, I forgot. Welcome back to the Calculus Fun Room. We have been discussing up to this point series and all the different types of tests we can use to determine whether the series converges or diverges. Now, really what's most important, what's most relevant for our conversation is when a series converges. That's really what we care about. And of course, the applications we look at, we're going to have situations that a series diverges on particular domains. But anyway, I'm getting a little ahead of myself. So in this video, I want to discuss power series in a kind of general form, and then I want to look at some examples. So start off really with an example of the sine function. So we can use a power series to represent the the sine function. So I'm going to write out the first couple terms of the series for sine. That's a plus symbol there. So if I have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. So the general terms of this series are negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So if n starts from 0 to infinity, we would get those terms. So if I plug in n equals 0, negative 1 to the 0 is positive 1. If I plug in n equals 0, I get x to the 1. And again, n equals 0, I get 1 factorial. If I plug in n equals 1, I get negative 1 to the 1, which is negative. So we can see that next term is negative there. When n is 1, I get a 3 as an exponent and a 3 factorial. So, 2n plus 1 represents all of the odd numbers when n is a whole number, positive integer, and then 2n represents all of the even numbers. So here is the power series, is what we call this for sine function, right? And the reason we call this a power series is because it's powers of x. Now, if I were to plug a particular value of x in here, let's suppose I plug in x equals 1 radian, I'm going to get 1 minus 1 cubed over 3 factorial plus 1 to the 5th over 5 factorial, and that takes this power series, or that takes this series back to our prior conversations. So in all of our prior conversations, we talked about the integral test, comparison test, ratio test, things of that nature. We never saw x's in those series. We only saw numbers, 1 or let's say like 2 to the n over n factorial kind of stuff back in those prior videos. So in this case, I'm showing you the sine series and saying to you that if I plug in a specific x value, it takes us back to our prior conversation. So one of the main conversations in this video and the next couple videos is what values of x would make this series converge. So for example, maybe when I plug x equals 1 into the series, I find out that it converges, and then maybe when I plug in x equals pi, I find out that it diverges. So what we're looking for is, where does this series converge? Now, I can think about the sine function being approximated by just the first term in that series. Or I could think about the sine function being approximated by, the first 2 terms in that series. Or I could think of the sine function as being approximated by the first 3 terms in that power series, and so on and so forth. Now, obviously, the more terms that I use, the better the approximation will be. And then as we add infinitely many terms to the series, we will get exactly equal to the sine function. So anytime I use just a finite set of those terms, then I'm getting an approximation. The more terms I use, the better the approximation. Now we're ultimately, and not in this video yet, I'm saying it to you, but forget what I said, we can call those Taylor polynomials. So this first example, sine x being approximated by x, that is a Taylor polynomial. It's a polynomial. It's a first degree polynomial. This second one, x minus x cubed over 3 factorial, this is a third degree polynomial. So in the video for 1110, we're going to just call that a Taylor series. And a Taylor series is just a power series for a specific type of function. All right, and now what I want to do real quick, I'm going to kind of visualize what this convergence means for a power series. So I brought up Desmos, and if I click the top left corner, the three little dots, I scroll down to the bottom. Under the calculus heading, there's Taylor expansion. So I'm going to go ahead and open that graph. And here is my Taylor expansion for the sine function. And you can see the series that we typed in here. And the series that they're giving me starts at 0 and goes to the number a. So, in other words, I am looking at my series here of going from 0 to infinity. So they're letting the upper number be a specific, they're letting the upper limit of that infinite sum be a specific number a, and I can prescribe what that number is. Now, we typically, I don't know why these go a, b, and negative, but we don't look at values of n that are negative. So I'm going to click here and let's let n start at 1. So we're going to go from 0 to 1, and let's say we go out the 10 terms of this series. All right, now actually I want to look at, let me click that again. I want to start at n equals 0 because I just want the first term in my series. Okay, so let me drag my a back to there. All right, so here is the first term in my series, n equals 0. And again, when n equals 0, if I plug 0 into this, I get just this first term, x. So that first degree polynomial sine is approximated by x. So the sine function is approximated by the line y equals x, and that's what we're seeing visually here. Right? So my sine function is approximated by y equals x. Now we can notice in this visualization that this approximation is pretty good when we're close to the origin. Right? What does pretty good mean? Well, I don't know. Looks like out here, well, here's x equals 1. Looks like at x equals 1 radian, we get a little bit of error here. At x equals like half a radian, those are almost indistinguishable. All right, now if I add the next term in my series, let's go out to n equals 1. So I now have the second degree polynomial. So here I am, when n is 1, I have x minus x cubed over 3 factorials. If I come back to that graph, here's that cubic polynomial estimating the sine curve. Now what we can notice, let me back up for a second, the interval where this polynomial approximates the function spreads a little further, right? So for example, if I look out here at, let's stick with x equals 1, I got a little bit of error there. Now when I add on that cubic term, there's almost no error there now. So we can see the x's for which the polynomial approximates the function well enough, right, is spreading. Now if I look at the next term, so here's my 5th degree polynomial, and notice how that's spreading even further. Here's the 7th degree, the 9th degree, the 11th, the 13th, and we can see that convergence spreading and spreading. So the more terms I add, the better the approximation to the sine function. When I look at the infinite series, it's exactly equal to the sine function. So if I were to keep going and going and going forever and ever and ever, we're going to see that convergence spread, and we're going to get exactly the sine function. So it's just really cool visualization here of where we can see, let me hit the play button, where we can see as we add more and more terms, that convergence spread. So we get this polynomial, this sum of polynomial terms that are approximating the sine function. That is really cool. I hope you're excited by it. You're probably sitting there going, oh my God, my mind is blown. And it should be. Right? So what we will do in the next couple sections, so we will look at some applications where approximating a function like sine would be relevant, would be really convenient for us. And we're going to look at really in I think 11.10, what functions have a Taylor expansion, or what functions have a power series approximation. We see here that sine does, right? What other functions do? Does cosine, does e to the x, does ln of x, right? And we're going to take that a little bit deeper as we look at some more application. All right, now in a more general form, right, what we just looked at was really a polynomial, right? Powers of x. So in a general manner, we can have some function be represented by a sum of terms. So we could have a constant, let's call it c sub 0. We could have c1 x to the first So we have the first degree coefficient, x to the first, the second degree coefficient, the third degree coefficient, so on and so forth. So again, in a generic form, what we're looking at is the nth coefficient of the nth degree term. Now this again is the generic form, so we can have a polynomial that has all of the degrees of the polynomial, right? And for the sine curve, we only had the odd exponents. Let's not get bogged down with why that one only had odd exponents. We'll come back and look at that a little deeper in the next video. But in a more general fashion, right, here is the power series, right? So again, these c sub n's, those are just my coefficients. These are the coefficients, right, of all of my polynomial terms. All right, now we could even more generally center our series at a place other than 0. So what I'm going to do here is instead of having x or x squared or x cubed, what I'm going to write is in a more general form. We have c sub 0 plus c1, I'm going to say x minus a to the first, c2 x minus a squared, c3 x minus a cubed, plus so on and so forth. Squares and cubes aren't coming out. So this, in an even more general form, are the coefficients that we have, and then x minus a to powers. Now in the prior general form we wrote, really the a number was 0. Right? So this is called the center of the series. So this is where the series begins its best approximation. And when we think back to the sine function, right, let me bring that graph back up real quick. When we look at our sine series doesn't have, x minus 1 cubed here. Right? It just has like x minus 0 cubed. So my series is centered at 0. So again, when we look at the graph, the convergence starts at x equals 0 and spreads from there. Right? So that's the significance of the center of the series. Okay? So we can write in an even more general form, centering the series at some number a. And again, for my sine curve that we just graphed, that a value was 0. So we say that, this is the power series centered at a. Centered at a. Okay, so even though this is the most generic form, let's play around with the one that we wrote a second ago, just to kind of get our hands dirty, make sense of this a little bit more, and then we'll come back again and abstract to that more generic form. So I'm going to take a look at this form here, where we have, the series centered at 0. We have coefficients and powers of x. And the first one I want to look at is, let's consider, so I'm going to rewrite the general form. That was c sub 0, c1x plus c2x squared plus so on and so forth. So let's consider where the c sub n's are all 1. So let's take a look at 1 times x to the n. So if I have all the c sub n's being 1, right, this is just 1. So again, x to the 0 is 1. There's my first term, and then I'm going to have plus x squared plus x cubed, so on and so forth. So if we look at this particular power series, right, just like I mentioned a couple minutes ago, right, we could plug in a specific value of x, and then this takes us back to all of those prior videos. So let's suppose we plug in, suppose we let x equals 1/2. Right? So the series that we have in that situation is 1/2 to the n, and going from 0 to infinity. And we can see that's going to be 1 plus, right? Again, my x is 1/2. Right? And again, my x is 1/2, so I get 1/2 squared and 1/2 cubed plus dot, dot, dot. Now we should recognize this as geometric. So plugging in a specific value of x, this is just like a geometric series back in our video for 11.2. And we know that this is a convergent geometric series, right? This is geometric. with r being 1/2. So since my common ratio is less than 1, it converges, right? So this converges. Okay, so I might ask the question then, let me scroll back up, right? What values of x will make this series here converge? Right? So when I pick the c sub n's to be 1, right? What values of x will make that series converge? And by plugging in x equals 1/2, we can say, we have found one value of x. Well, what other values of x will this series converge? Well, if we, let me back up a second. So we plugged in x equals 1/2 here. What if I plug in x equals 3? So what if x equals 3? Right, so then we get the sum of 3 to the n, and that's 1 plus 3 squared, 3 cubed, so on and so forth. And again, that is geometric. And the r, an absolute value, is 3. That's greater than 1, and so that's divergent. Again, that shouldn't really be a surprise in the sense that the base of this powers of x is bigger than 1. That's a divergent geometric. And when that base is less than 1, it's a convergent geometric. So if I come back up, let me scroll back up for a second, and I look at this power series right here that I boxed in, what values of x will make that series convergent? And we know as long as x is less than 1, that's a geometric where the ratio is less than 1 and it's convergent. So I'm going to write that down, and I'm going to say since the sum of x to the n, my infinite series, since that sum, I'm going to go ahead and write it out just to point out to ourselves, right? This is geometric. Since this is geometric, with common ratio equal to x, right, comma. Right. So again, when I thought of geometric back in 11.2, I saw like a multiplicative factor, right? Like, so what do I multiply the first term by to get the next term? And that's x in this example. And then I multiply that term by x to get the next term, x squared, and multiply by x again to get x cubed, right? So there's my common ratio of x, right? And this converges when that common ratio is less than 1. So we can say minus 1 less than x less than 1. So on this interval right here, this interval of domain is when that series converges. Right? So if I were to take out my Desmos and graph it, and I'm not going to do that at the moment, I will come back and do that in a couple minutes, we would see this is where the convergence lives, if you will. Right? This is the domain of the power series for which it converges. Now we don't want to look outside that interval because then it doesn't make sense to consider a divergent series. So I'm really only interested in this power series for within the interval of convergence. Now I ask the question, right, what does this power series, what does it equal, right? What is the function that it equals, or what is its sum? So the very first example that we looked at, we had x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus ... and that sum equaled sine of x. Right? So that whole infinite series equals sine of x. Now in all of the prior sections, there was only one series that we could find the exact sum of, and that was a geometric series. All the other sums that converged, so sums that converged by the integral test, we could only estimate those summations and then look at the bounds of the error, right? What was the maximum error? When we had a comparison test, we could sum up the first 20 terms of that series and estimate the infinite sum, and then we had, maximum bounds of error. What we really want to do in this section is consider what does this sum equal exactly. We want it to represent a function. So just like sine x has a series representation, what does this series represent? What function? All right, anyway, so since it's convergent geometric, so let's recall, right, that a geometric series the sum of AR to the n, right? A plus AR plus AR squared plus dot 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 has the sum that is A over 1 minus R. And again, that's only where it's convergent. Does the sum make sense? So for our example that we're looking at here, this power series, my common ratio is X. Right? That's my common ratio, R. So I'm going to replace R with X down in this expression. And the A in this expression is the first term in that series. So the first term in my power series up here is 1. So my A is 1. My R is X. So for our example, A is 1 and my R is X. So here's the sum of my series, 1 plus x squared plus x cubed plus dot dot dot. The sum of the series x to the n from 0 to infinity is 1 over 1 minus x. All right, now what does that mean? Okay, so in our very first example, we had that the sine of x equaled its Taylor polynomial, right? Its power series. Now we have the function 1 over 1 minus x has a power series. So far we see two functions, sine x and 1 over 1 minus x, that have a power series representation. Now again, I know you're really excited and you're really curious and you're asking yourself, well, what other functions are there that have power series? And I'm saying to you, hang on now, hold on, slow the horses. We're not going to go down that path just yet. All right, we're going to do that in the next video. But for now, we see two functions that can be represented by a power series. Now what our conversation really is in this section is, where does this series converge? So we saw in the calculator in Desmos that the sine function converged everywhere, right? All reals, and we're going to come back and test that in a second. And we know exactly that this power series here converges when x is less than 1. So I'm going to come over here and scribble, right, x less than 1. That's when this sum, right, when this function has a series, that's when it makes sense. That's when it's defined. That's where it converges. All right, now again, our question in this section is, where does the series converge? So where does a power series converge? That's our bigger question here. Where does a power series converge? Now we already answered the question. Again, I'm going to repeat myself. We already answered the question that this series converges on the interval -1 to 1. Right? But what about the sine series? Let's come back and look at the sine series. Right? Where does it converge? Right? Again, I already kind of wrote down the answer that we saw earlier. Actually, I didn't write it down. I just said it verbally. We saw on the graph it was started to converge for all reals. The convergence started at 0 and spread and spread and spread. Right? Let me bring up that graph. So my convergence starts at 0 and spreads and spreads and spreads. Right? Now what I'm going to do here before I answer the question I just wrote on the board is let's look at the geometric series 1 over 1 minus x. Now we said it only converges between -1 to 1, so let's see what that looks like. So the function that I'm using here is 1 over 1 minus x. So I'm going to come up to Desmos, and I'm just going to delete the sine curve and do 1 divided by 1 minus x. And then my series I need to change. Again, if I come back to here, my series is just x to the n. There's no alternating term. The coefficients are all 1, so there is no alternating term. Let me get rid of that. And then I just have x to the n. So I just have x to the n, and then I don't really have anything in the denominator. It's just 1, right? So there's my series, right? Now let me turn that off for a second. So here's my function 1 over 1 minus x. Here's that function, and it's being graphed for all reals except for x equals 1. Now we know that this series converges between -1 and 1. All right, now this series was centered at 0. Again, we talked about like x minus 0 to the n was our center of our series. I'm writing with the mouse. That's really sloppy. So as we start to graph this convergence will begin at the origin. Now as I add on one term, oh, I got to graph it. Goofball. All right, so the convergence begins right here at the origin, and we can see it's not a very good approximator to the function, slightly away. But let me add the next term, and we can see the convergence spread a little bit from the origin. Let's add the next term, and we can see the convergence spread even further from the origin. Here's the next term, and 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 so on and so forth. And remember, the convergence, the interval of convergence was only -1 to 1. So this infinite polynomial is only going to approximate this function in that interval, -1 to 1. So we can see between 1 and -1, we're getting very good approximation. Outside that interval, it's a divergent series. So it doesn't approximate the polynomial very well outside that interval. Now, how useful is that? That's a question we're going to answer later. Right? But what we're concerned about at this point is, where does that convergence live? Right? What is the interval of convergence? So again, 1 over 1 minus x has the power series x to the n. Its interval of convergence is -1 to 1. So where does the sine series converge? Now again, we saw on Desmos that it's all reals, but let's see where that comes from. So what we're going to typically do in this section is almost exclusively use the ratio test, right? So let's do that here. Let's use the ratio test. And let's watch how really cool this becomes. Let's use the ratio test. Now remember, the ratio test was, I'm going to take the limit of the ratio of any pair of adjacent terms, and I'm going to investigate this limit. Now for convergence, I want less than 1. So for this power series, I only care where this limit is less than 1, because I only care about convergence. I don't care about anything where this series is divergent. So this is what I'm really interested in. So I'm going to come back up here to my series that we wrote. I'm going to plug in n plus 1 into every n value that I have here. And then I'm just going to divide by the nth term. So let me scroll down. So I'm going to plug in n plus 1. So I have -1 to the n plus 1, x to the 2 times n plus 1 plus 1 all over 2n plus 1 plus 1 factorial. And then I divide all of that by the nth term. So I get -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. All of that in absolute value, and I'm looking long term out at the ends of the series, right? Limit as n goes to infinity. Now, after we've done a whole bunch of problems in the section where we had the ratio test, I honestly don't really want to write this first step. I don't really want the compound fraction. So all of the other problems here, I'm going to jump right to the flip and multiply version. I don't really want to deal with this here. Now, let me go ahead and do that, and I'm going to have to write kind of tiny. Let's flip and multiply, and I'm going to simplify these expressions here. So I really have -1 to the n plus 1, and this is really 2n plus 2 plus 1, which is 2n plus 3 all over, and that's 2n plus 3 factorial. And then I flip and multiply, right? So I have 2n plus 1 factorial over... I'm going to have -1 to the n, x to the 2n plus 1. Right? Now, technically, all of this is still in absolute values, and I have the limit as n goes to infinity. Now, remember, the really cool advantage to the ratio test here is it deals with factorials and exponential terms really nice. Right? So watch what's about to happen. We're going to split up all of these exponents. We're going to split up the exponents. We're going to split up the exponents. And we're going to split up the factorials. So all of the exponents I have right here, I'm going to write this as negative 1 to the n times negative 1 to the 1. I'm going to write this as x to the 2n times x to the 3. And I'm going to do the same thing down here. So I'm going to have negative 1 to the n times negative 1 to the 1. I'm going to have x to the 2n and x cubed. And then I'm going to go ahead and take the polynomial terms over here. Right, this is just kind of how I like to organize. And then I have x to the 2n and x to the 1. Right? So I took the negative 1 to the n and just kind of reorganized it. X to the 2n times x to the 1 here. And then I'm going to have the factorials. Now, I'm going to hold on to the factorial for a second, and we're going to talk about how to deal with that, just like we did back in the section for 11.6. So I have the absolute value of all of this and the limit as n goes to infinity. Now we can see the negative 1 to the n's are going to cancel here. Oh, that's right. Negative 1 to the n's. Sorry. And then I have x to the 2n's are going to cancel. And in fact, x cubed over x to the 1 is going to become x squared. So I'm going to come over here. I'm going to start to write kind of small. So I have an x squared left over out of all of that. And then, all right, you know what I'm going to do as well? I'm going to go ahead and apply the absolute value. So the absolute value of negative 1 is positive 1. So I'm going to go ahead and get rid of that absolute value because I have just applied it. Now also, the x squared that I'm left with here, that's always positive. So I don't really need the absolute value anymore because any x squared is positive. So I've applied the absolute value there. Now, what do I do with the factorials? Now, remember what we talked about in the prior video, that in order to get factorials to cancel, I'm going to peel off each prior term. So, this factorial in the denominator is a little bit bigger than the one in the numerator. Okay, so in order for these to match, I'm going to peel off the terms in the denominator. So in the denominator, I have 2n plus 3 factorial. So in the top, I need to match that. So what I'm going to do is peel the first term off here. That's going to give me 2n plus 3. And then, if this is, so let's suppose n was 5. This gives me 5 times 2, which is 10 plus 3. So I get 13 factorial. So I'm going to subtract 1 from that to get 12 factorial. So 2n plus 1, I subtract 1. I get 2n plus 2. And then I subtract 1 again and get 2n plus 1. And I'm going to stop there so that the 2n plus 1s cancel. And then I really am left with, in the denominator, 2n plus 3 times 2n plus 2. So everything I'm left with at this point is I have x squared over, and I got 2n plus 3 times 2n plus 2. All right, now I'm going to apply the limit. Now the limit is only working on n. So I only need to concern myself with the expressions that have n. So for the moment, the x is constant. Now granted, x is variable, I know, but in terms of the limit process, it's not involving any n's at all. So I'm going to only look at the expressions with n's and let n go to infinity. Now as n goes to infinity, I have something constant over something going to infinity. All of that goes to 0. So this whole limit turns out to be x squared times 0. Now, all right, I know that that is 0, but I want to stop for a second and not jump to that. So all of this stuff that we just evaluated comes out of the ratio test. And in order to show convergence, we want all of this stuff out of the ratio test to be less than 1. All right, so I'm kind of asking what x is, right? Where does this happen? For what x is? Okay. Now in this case, any value of x is going to work, right? If I pick x equals 5, 5 squared times 0 is 0, and that's less than 1. If I pick x equals negative 3/5, right? Negative 3/5 squared times 0 is less than 1. So for what x is my ratio test less than 1? Well, for this particular example, for all x's, okay? For all real numbers, okay? So we're going to say the interval of convergence is minus infinity to infinity, right? There's all reals, that series converges. And then again, we knew that already. We looked at the graph, we saw the sign converge and spread from the origin and keep going and keep going and keep going. Right? So we knew that was the result. But this is what the result would look like through the ratio test. So this is the main conversation in this section. Where does a power series converge? And typically to answer that question, we're using the ratio test. We're going to almost always exclusively use the ratio test. Now there's one or two exceptions to that rule, but 99.73% of the time, the ratio test will work very nicely for us. All right, I want to do a couple more examples and we're going to summarize what we've been talking about here. So my instruction, I want to say find the interval of convergence for the series. Let's say we have x minus 3 to the n over n. This n goes from 1 to infinity. All right, I can't start this at n equals 0 because then I have division by 0. I mean, I'm going to start it at 1. Now, again, we're taking our focus away from, what function does this represent? I don't know if this represents, cosine or ln of x. And at this point, I don't care anymore. We're going to care in the next video. For now, I'm just focusing on where does this power series converge? Now, this is completely not necessary, but I could write out the terms of this series. Right? The terms of this series would be x minus 3, and then I would have x minus 3 squared over 2, and x minus 3 cubed over 3, and so on and so forth. At this point, I'm really not concerned about what the series looks like. We'll come back to that in the next video. But I am asking, where does the series converge? So again, I'm going to use the ratio test, and I want to know where does the limit of the ratio of any pair of adjacent terms, right? Where is that limit 1, right? When is this, right? For what value of x, right? That's what we're asking. All right, now I'm looking at my power series that I wrote here, and I'm going to plug in n plus 1. And then I'm going to divide by the nth term. Now I'm going to not write this compound fraction. I'm going to go ahead and flip and multiply my expression. And I'm scrolling my series out of my picture here. But so when I plug in n plus 1, I would have x minus 3 to the n plus 1 all over n plus 1. And I have an absolute value, and the limit is n goes to infinity. And then when I flip and multiply, that's n over x minus 3 to the n. Now, all the exponential terms clean up really nice. Notice I have no factorials here, but I have these exponential terms, right? So I'm going to split this. I'm going to write this as, x minus 3 to the n, and then x minus 3 to the 1, and then I have the n, and then I have n plus 1, and I have the x minus 3 to the n. And again, the nice thing about the ratio test is the factorials and the exponential expressions clean up very nice. So in this case, what do I have left? Let's see, I have the limit of, and I'm going to write, what I'm going to do? I'm going to pull the polynomial terms together. So I have n plus 1, and then I have absolute value, I have x minus 3 to the first. All of that in absolute value. I don't want that to look like it's connected. Let me pull that away. All right. So here's my simplified version of my ratio test. Now I need to apply the limit process after doing the algebra cleanup that is available. So just like in our last example, the x expression that I have here, x minus 3 to the first, has no n values. I don't have x minus 3 to the power of n. So as far as the limit process is concerned, I can pull that out. Now, x might be able to be negative. Right? What if x was negative 1? What if negative 1 was a point of convergence? So I want to be careful. If I have negative 1 minus 3, that's negative 4. I want to take the absolute value of that. So I'm going to leave the absolute values attached to that x expression because it could be negative. in some situation. Now I'm going to evaluate this limit. Technically, this is L'Hopital's rule. It's infinity over infinity. If I take the derivative of the top, derivative of the bottom, I get 1. So this whole limit turns out to be x minus 3, times 1. This limit is 1. So the final question of the ratio test is, when is this less than 1, right? This is the result of my ratio test. And when is this less than 1, right? What values of x make that true? So now this becomes basically solving an algebraic equation. So absolute value of x minus 3 less than 1 is equivalent to saying the compound fraction that x minus 3 is between minus 1 and 1. I'm going to add 3 to all pieces of my inequality. So negative 1 plus 3 is 2. And then 1 plus 3 is 4. So this is my interval of convergence. So any values of x between 2 and 4, my series that we had, x minus 3 to the n over n, will converge. Now, hang on. We're not officially finished with this problem, and we're going to talk about why. So I'm going to say has interval of convergence 2 to 4. Almost. Now, here's what we have to do. Here's what I mean by almost. Let me put n going from 1 to infinity. Here's what I mean by almost. Look back up here. I'm going to circle this in green. I like green. Here's the result of my ratio test. Now, if I plug in x equals 2, I get absolute value of 2 minus 3. Absolute value of negative 1 is 1. And 1 is not less than 1. Now, in the language of the ratio test, when I plug in x equals 2, my ratio test provides a limit of 1, and that's when the ratio test is inconclusive. Remember, we talked about that in 11.6. So the ratio test gives me a result that's inconclusive at this endpoint of x equals 2, and that will always happen. At the endpoints, I will always get an inconclusive result from the ratio test. In fact, if we plug in x equals 4, we see the exact same thing. If I plug in x equals 4, I get 4 minus 3, which is 1. Absolute value of 1 is 1. So the ratio test at x equals 4 is producing a limit that is 1, and it is therefore inconclusive. So does that mean my series diverges there? Not at all. My series might converge at x equals 2, and therefore it's conditionally convergent. But in this section, I don't care if it's conditional or not. I just want to know if it converges at 2 or 4. So here's how we're going to answer that question. This is not overly difficult. We're going to take x equals 2, and we're going to plug it back into my series that I am testing. And I'm going to ask, is that convergent or not? Remember, when I plug an x value in, I'm taking myself back to all of the prior conversations that we had. So I'm going to say, what if x equals 2? Right? What behavior do we get? So if I plug x equals 2 back up in this series, I get 2 minus 3, which is negative 1. So I get negative 1 to the n over n. And we know from our prior sections, this is the alternating harmonic series. Now, there's going to be problems in the homework where this is not an obvious series like alternating harmonic series. I might have to use the alternating series test here, and that's okay. I've done that in 11.5. I'm comfortable with the alternating series test, and I would use it if I have to. There might be a situation where this series needs the, comparison test or limit comparison test. Or I might even see this series have terms that don't go to 0, and so I say the divergence test tells me that it's divergent. But this particular example is the known alternating harmonic series that converges. All right? So, in other words, when I look at my interval of convergence up here, at x equals 2, I'm going to put an or equal to. So I'm going to scribble that in green as an or equal to. So let's come back. Let's plug in x equals 4, and let's see what we get there. Are we going to include x equals 4, or are we not going to include x equals 4? So I'm going to mimic the same process I just did here for x equaling 2. So I'm going to take x equals 4 now, plug it in my series up here, get 4 minus 3, which is 1, to the n over n. So when I plug in x equals 4, right, so if x equals 4, what we end up with is 1 to the n over n. And, keep in mind 1 to any power is just 1. So I get 1 over n. And this is a p-series, right? This is a divergent p-series. Right? The p is equal to 1, which is less than or equal to 1. Right? So that's a divergent p-series. Now what that means is x equals 4 I don't include in my interval of convergence. So we initially had, right, so I'm just going to switch back to blue here, right? So we had the interval of convergence being 2 to 4, and we now know, after testing the endpoints, we now know after testing the endpoints that the interval of convergence is 2 less than or equal to x. Right? Oops, not less than or equal to 4, strictly less than 4. Okay. All right, now again, this example shows me that the ratio test might give me a finite interval, like 2 to 4. So the sine series gave me an infinite interval, right? Minus infinity to infinity. But when I have a finite interval, I need to test the endpoints. All right. Now, if I think back to this other example that we had, let me scroll back up here real quick. The very beginning example after we did the sine function was 1 over 1 minus x. Where did this guy go? Here we go. So 1 over 1 minus x. Now, the reason we did not test these endpoints is because we didn't need to. This was a geometric series. We already know that at 1 and minus 1, the geometric series is divergent. So we don't consider that having to test the endpoints. Right, now if I wanted to, and I'm not going to, but if I wanted to use the ratio test on this series, x to the n, I would then have to test the endpoints. So I'd have to plug in -1 and look at -1 to the n, and plug in +1 and look at 1 to the n, and I would test those values. But that would be very inefficient. I recognize this as a geometric series. I don't want to go through that work. All right, let's take a look at one more example, and then I'm going to kind of summarize what we've discussed here and look at one other really cool application. So let's say we're given this power series in factorial x to the n, and we want to know, what's the interval of convergence, right? So the instructions would say find the interval of convergence here. No, we don't have to do this in this case, but if I wrote the terms out, I would get 0 plus 1 times x plus, I would get 2 factorial x squared, 3 factorial x cubed, so on and so forth. The reason that I wrote this out, I wanted to point out to you that we define 0 factorial as being 1. All right, now that seems weird. You're like, well, why can 0 factorial be 1? Bear with me for about 2 minutes here. I'm going to go off on a little tangent. Boom, boom, pun intended. So a factorial is in a statistics course, let's say, or a probability course, or a course on counting techniques. Factorial can be defined or thought of or explained in the following way. So it describes how many ways we can order indistinguishable objects. So for example, let's suppose we have the 7 Harry Potter books, and we want to place the Harry Potter books on a bookshelf. And I want to consider them in an ordered manner, right? So let's say I have 7 slots, 1, 2, 3, 4, 5, 6, 7. So I'm going to place Harry Potter books in those slots. Now for the first slot that I'm going to fill, I have any one of the 7 books to place there. So how many choices of books do I have for this first slot? I have all 7 books, choosing one of those 7 to pick from. Now, once I place a book there, I only have 6 books left to place in that second slot. And then once I've placed 2 of the books, I only have 5 books left, and so on and so forth. So how many ways are there for me to order 7 distinguishable books? There's 7 factorial ways to do that. So a factorial in a statistics class, a probability course, a counting theory class, can be used to count how many ways to place, how many ways to order indistinguishable objects. So the 0 factorial, right, where does that come from? So 0 factorial is basically saying how many ways are there for me to order none of the books. And there's only one way to do that. I don't place any of the books. So that's one way to think of 0 factorial as being 1. How many ways are there for me to place none of the books on the shelf? There's only one way. I don't grab any of the books. So we define 0 factorial as being 1 in that same conversation. So this first term that we had here, when n was 0, 0 factorial is 1, and then x to the 0 is 1, and I have a typo there. That was supposed to be 1, right? So I get 1 plus x plus 2 factorial x squared, so on and so forth. All right, so back to the question here. Where does the series converge? So we're going to use the ratio test. And again, I'm looking for what values of x make this less than 1. So I'm going to work through this whole limit like we've been doing, and the last thing I'm going to do is say, where is that less than 1? Now for this particular example, the plugging in n plus 1, I get n plus 1 factorial, x to the n plus 1, and then I divide by n factorial x to the n. Now, I'm not really doing a flip and multiply here because I don't have a compound fraction, but I'm going to split stuff up. So I'm going to do a bunch of splitting simultaneously here. Just I want to be efficient. So when I look at the factorials, the larger factorials in the numerator. So I'm going to peel off the first number in that factorial and leave the rest in a factorial form because that's going to cancel nicely with the 1 in the denominator. And then the x to the n plus 1, I'm going to split up that exponential form. And again, the reason I'm going to do that is because the x to the n's cancel out, simplify rather nicely. So I really have the limit as n goes to infinity of the absolute value of n plus 1 times x. Now, remember what we've said a couple times is the x doesn't have any n's attached to it, right? So in other words, the limit of like f times g is the limit of f times the limit of g, but x, the limit of x as n goes to infinity is just x. So that's in essence constant as far as the n's growing without bound. Now I'm asking, when is this less than 1? So what is this limit? So n plus 1 as n goes to infinity goes to infinity. And I'm asking, where is that less than 1? Right? So what values of x make this less than 1? Okay, so there really isn't any values of x except for x equals 0, right? But any other x that I pick, if I pick x equals 5, 5 times infinity is infinity. Now again, this is really sloppy notation. I can't say 5 times infinity. Infinity is not a number. I'm really looking at the limit here, right? So if I pick x equals 5, I get 5 times the limit of n plus 1, and that's infinite, and that's not less than 1. If I pick x equals negative 2, let's say I pick x equals negative 1/2. So negative 1/2 absolute value is positive 1/2 times the limit of n plus 1, which goes to infinity. That's not less than 1. So the only time I get something less than 1 is if x is 0. So the only time 0 times infinity is less than 1 is if x equals 0. All right, so I want to summarize everything that we've seen up to this point. And then one other thing I want to talk to you about. So the series that we've looked at so far, the series that we've looked at so far, we saw the sine series. And again, I don't really care about the function at the moment. We saw -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. That was my sine series. N went from 0 to infinity. And then where did it converge? Right, so where did it converge? It converged for all reals. All right, now a couple of the theorems in the next couple sections, we're going to have some theorems that reference the radius of convergence. And if I think about this as, shading numbers on a number line, half of the interval is the radius, right? So let's say the distance between these two endpoints is the diameter, half of that distance is the radius. So we'll always say the radius is infinite when the interval of convergence is all reals. Now what was the other example we saw? It was like x minus 3 to the n over n. N went from 1 to infinity. And that interval of convergence was from 2 to 4. Now, if I think about, the distance between the endpoints is 2. So half of that is the radius. Okay. Now, the radius doesn't change whether I include or don't include an endpoint. The radius is just 1 in this case. The other series that we looked at was the sum of x to the n. And again, that was that represented the function 1 over 1 minus x, which is not our focus here. And because that was geometric, we knew its interval of convergence was -1 to 1. And again, that radius would be 1. And then this last example we looked at was n factorial, x to the n. And it only converged at x equals 0. So, technically, I wouldn't call that an interval of convergence. It's just a singular value of x. It's a singular point. And so there is no distance. This is not an interval. So there's no distance between endpoints. So we're going to say that the radius is 0. All right, so I am borrowing this out of Stuart's textbook and giving him credit. Thank you for typing this up for me, Stuart. I did not want to have to write this out just to save a little bit of time. So there is a theorem, there's a result in every calculus book within this conversation that basically says every power series converges. Every power series converges. It's only going to converge in one of 3 possible ways. So the first way it could converge is only at a singular point at x equals a. So if we center the series at a, when I plug in x equals a, I get a minus a, which is 0 to the n. So if it only converges at a, what I really have is 0 plus 0 plus 0 plus 0 plus 0 plus 0, which is not a very interesting series. But the series does converge. And if we're just talking about a general form, general conversation, every power series converges. The weakest type of convergence is at a singular point. Those aren't very interesting. Now, we could have a really awesome result that the series converges for all reals. So like our sine series, it converges for all reals. Now, this is really awesome. We love when we find this result, because then we can use that polynomial to approximate that function anywhere we want for any x value. And then kind of the middle ground was the couple examples that we saw here where we had an interval. Right? So we had this example, x minus 3 to the n over n, that had a kind of a finite interval of 2 to 4, and then x to the n was that geometric series from -1 to 1. So that's what number 3 is illustrating, or I should say those examples illustrate the general conversation in number 3. So number 3 basically says, between minus r and r, so if x minus a is between minus r and r, that's where the series is going to converge, some finite interval. And then there is a radius of convergence. I want to point out to you in this theorem here, there is no or equal to sign. So again, whether I have convergence at the endpoint or I don't, that doesn't change the radius. So the radius is the radius is the radius, whether there's convergence at those endpoints or not. Now, within the context of this section, you will be expected to determine whether there is convergence or divergence at an endpoint. But in regards to this theorem, the radius of convergence is the radius of convergence, whether the endpoint's included or not. So every single power series converges either at a point, which is very weak and not interesting, for all reals, which is really awesome, or over some interval of values. So I just want to have a conversation about one last example here, and I'm looking at Stewart's textbook, page 748. This is a really cool example to just show you some of the applications of power series. Now, I've mentioned to you that we can use a power series to estimate a function, and that is true. And we will look at some really cool applications of that shortly in the next couple videos. But before you get to that conversation that sine of x has a power series, Stewart hasn't had that conversation yet. So he presents to you a different application, which involves what we call a Bessel function. Now, I'll just read this paragraph here for you. It says, we'll see that the main use of a power series is that provides a way to represent some of the most important functions that arise in mathematics, physics, and chemistry. In particular, the sum of power series in this example, or the next example, is a Bessel function. It's named after the German astronomer Friedrich Bessel. And the function given in exercise 35 in the homework is another example of a Bessel function. These functions first arose when Bessel solved Kepler's equation for describing planetary motion. Since that time, these functions have been applied in many different physical situations, including temperature distribution in a circular plate and the shape of a vibrating drum head. So a lot of times, things that kind of have wave form or wave behavior on a constrained domain, like a plate or a drum head, we can use Bessel functions to model those behaviors. So if you look at the graphs over here on the left, here's a photo of a vibrating drum head, and we can see that if we graph this Bessel function in the three-dimensional space, we get this graph that we see down here below. And the graph here is representing pretty much what we see in this picture above. We can see how the wave would propagate from hitting in the center, and then the wave travels and hits the boundary and then flows back and begins to cause disturbance on itself. Or you think about when you jump in a pool, the waves travel, they hit the edge of the pool, they come back, they get all crossed up, and they cause disturbance on themselves. Bessel functions are one way to model that behavior. Now, we have different orders of Bessel functions, and the one that Stewart presents to you is Bessel function of order 0. Now, the Bessel function of order 0, as we can see right here, is defined as a power series. This is negative 1 to the n, x to the 2n over 2 to the 2n times n factorial squared. Now, after showing you this example or this application of one particular power series, Stewart says, let's find the domain of the function. So let's find its interval of convergence. So just to show you the work that he goes through here, right, he uses the ratio test. So he looks at a sub n plus 1 over a sub n, and he sets up that expression. Notice he just flips and multiplies right away. He does some cleanup of all of the algebra here. Kind of skips a step or two, right? But if we were to fill in those gaps, you would see what we discussed. And then here's the end result. And as n goes to infinity here, so he's not even writing the limit as n goes to infinity, but as n goes to infinity, x squared is a constant. So just the way that we dealt with the variables in my examples, we pull it out. So really 1 over 4 times infinity squared, right? Constant over infinity goes to 0. So we have x squared times 0, and that's going to be less than 1 for all x. So the Bessel function of order 0 converges for all x. So minus infinity to infinity, as he mentions down here, is the interval of convergence, and then the radius is infinite. All right, so that concludes our conversation about a power series and determining where a power series will converge. I look forward to seeing you in the next video as this gets even more exciting.